doubt, the aircraft of today are much quieter, cleaner, and more efficient than the aircraft of the past.
That's true, but even as good as aircraft are today, we can still make them even better. Hey, I'm Johnny Alonso.
And I'm Jennifer Pulley. And today on NASA 360, we'll see how NASA and industry are working together to make the aircraft of the near future as quiet, clean, and efficient as possible. It's been a little over 100 years since humans took the first powered flight out at Kitty Hawk, North Carolina. And look how far we've come.
From the Wright brothers' first 120-foot flight to now being able to fly tens of thousands of miles in a single day, the science of flight has evolved quickly and continues to evolve every year. That still holds true today. Even though our current aircraft are incredibly efficient, future aircraft may make them seem like noisy gas guzzlers.
So what will aircraft of the near future, say within the next few decades, look like? Well, that's a question that NASA's Environmentally Responsible Aviation Program, or ERA, is trying to help answer.
NASA's ERA researchers have a pretty good idea of what the characteristics of near-future aircraft will need to have to make them more efficient and less noisy. But NASA isn't in the business of building planes. They will need to work hand in hand with the airline manufacturers to collaborate on bringing advanced concept aircraft out of the planning stages and into reality. Later, Johnny Alonso will be talking with some of NASA's industry partners. But first, I spoke with NASA's Environmentally Responsible Aviation Manager, Dr. Faye Collier, to find out a little more about what NASA's Advanced Vehicle Concepts program is all about.
Okay, Faye, so tell us what the Environmentally Responsible Aviation Project is all about.
Okay, so the Environmentally Responsible Aviation Project is a 5-year, 6-year project, and it's focused on advanced aircraft design and the technologies that are needed to enable them. The main goal of the project is to reduce noise, to reduce mission fuel burn, and to reduce LTO NOx emissions. And LTO stands for landing takeoff, oxides of nitrogen emissions. And we want to do that simultaneously, and that's never been done before, where we looked at some very difficult metrics and tried to push all of those metrics down simultaneously.
Why is NASA involved in aeronautics?
Well, Jen, the first A in NASA stands for aeronautics, and so we have a very, very long history going back to 1917, working this particular aspect of the work that goes on in the nation focused on aeronautics for the benefit of the nation.
Now, you talk about aeronautics. I mean, this is general public, on and off of airplanes all the time. We've been doing this for a while.
Yeah.
Technologically speaking, airplanes are pretty good.
Yes, they are.
Okay, so why the need for improvement? What kind of things need to be improved?
Well, that's a good point. So over the last 30 years, we've made a lot of improvement in the way aircraft fly in the air transportation system. Noise, for example, community noise, has been reduced by quite a bit since we first entered the jet age back around 1960. However, we believe that there are some future improvements that are still left to be had. There's still a lot of work that we can do. So one of the things we're looking at is this idea of integrated configurations, looking at wing body configurations that are more highly integrated to get a better result than we can with traditional vehicle designs.
And we are actually right here in a wind tunnel with this integrated design behind us.
That's correct.
And this
yes.
is so neat. Okay, so this is
Yeah.
kind of what you're talking about when you say, away from the tube and wing.
Right, and moving more toward a blended configuration to provide a completely different looking vehicle that can theoretically provide these bigger benefits over time. So that's what we're focused on.
So, Faye, recently NASA put out a challenge to the industry to do some advanced concept vehicle designs that is really going to change aviation. Talk to me about this challenge.
Yeah, so the challenge that we have put out recently has to do with looking at vehicle concepts that can meet these goals simultaneously. So there are 3 contractors. Lockheed Martin is involved, Boeing is involved, and Northrop Grumman is involved. Pretty soon we'll be reviewing final design concepts that will be coming from each of those 3 companies. The companies that brought in a couple of the engine companies, Pratt & Whitney and Rolls-Royce, are also involved with those studies, and so we're getting the combination of traditional airplane companies and engine companies bringing a lot to the table to help us solve this problem.
what happens next? I mean, after we get through this initial phase of the competition, then what?
Yeah, right. So this competition lasts about 12 months, and we'll get a public out brief from the 3 contractors, and that'll be very exciting. After that, we'll be digesting the data and all the learning that we've gotten from the conduct of the 3 studies, and we'll be looking into what to do next. That could involve taking a couple of the concepts to a preliminary design phase, which is sort of the precursor to actually building one of these vehicles.
And then NASA would be involved in all the testing that goes along with that.
Yeah, so the vision would be on that aircraft, think of it as an asset that NASA would have available for 20 years. We would use to test all kinds of technologies, not only the ones that it would come with initially, but then follow-on technologies. So we would make the aircraft it would be a testbed vehicle available to the community to test these advanced concepts on. And it would be something that would last a long time.
Well, Fay, I know we got to get this test on the way here, so
yeah.
Thank you so much for your time today. I really appreciate it.
It was a real pleasure. Thank you.
Thanks, Fay. Stick around. There's more of NASA 360 coming up after the break.
As Jen mentioned, NASA has a pretty aggressive goal to change the way we all fly. But to drastically reduce fuel burn, emissions, and noise, you have to design a drastically different vehicle. Luckily, NASA's working with 3 of the industry leaders to do this, including Lockheed Martin, Northrop Grumman, and Boeing. Each of the companies have come up with their own version of the advanced vehicle concept, and as you will see, their new designs completely rethink the way we'll be flying in the future. I came out here to California to meet up with these 3 companies to find out what their version of the advanced vehicle concept looks like. Up first, I'm in Palmdale, California at Lockheed Martin's famous Skunk Works facility. I will be speaking with Bruce McKay and Jeff Kramer, who will talk to me about Lockheed Martin's advanced vehicle concept. Bruce, recently NASA put forth a challenge to industry to come up with advanced concept vehicles. What exactly was the challenge?
NASA challenged the aerospace industry to find a way to reduce aviation's impact on the environment. They did that by defining 3 goals. 1, can we reduce fuel burn by more than 50%? Reduce the noise of airplanes to really contain the noise within the airport environment and reduce the emissions that are produced by the engines that power all these aircraft.
How is Lockheed Martin involved in this program?
The way Lockheed Martin is involved in this program is we are leading one of 3 contractor teams in developing the next generation airplane concept that can achieve the goals that NASA has put forth. So we have a number of subcontractors we are working with. We evaluate the technologies at the system level to ensure that we can achieve those goals. So as the system designer, we not only lay out the framework for the program and how the study goes, but we conceive those new designs.
There are 3 fundamental areas of airplane design that can be improved upon, and they really govern the overall efficiency of airplanes. One is the weight of the airplane, and going to composites, like today's new bicycles are all carbon fiber. If we put carbon fiber on an airplane, we can reduce its weight, make it lighter, it's more efficient. We're looking at a next generation engine which has a much larger diameter on the fan, and the industry is going in that direction, and that also improves efficiency. Aerodynamically, just like a glider, our box wing airplane concept, it's a non-traditional airplane design, uses 2 very long skinny wings which are aerodynamically more efficient than the traditional wings. So combining all 3 of these technology areas, we're able to achieve and meet the 50% reduction in fuel burn goal that NASA has established.
So what exactly do you mean by box wing?
A box wing airplane is like a biplane. It has 2 wings and we join them at the tips. The advantage is it can go much faster than the traditional biplanes, the 1920s and 30s. And the aft wing is actually mounted high on the airplane, which allows me to put a much larger, more efficient engine on it. The wings themselves are very skinny, kind of like a glider airplane, so I have much more aerodynamic efficiency from them. So I combine the aerodynamics with the more efficient engine, and that combined with the composites allow us to have a much more efficient airplane and actually achieve the NASA 50% reduction in fuel burn goal.
There are several ideas that we're looking at in terms of revolutionizing the efficiency and aerodynamics of the airplane. First one of the main ones, of course, is looking at what we call ultra-high bypass ratio engines, where we get about 20 to 25% better fuel efficiency with those. The next one is looking at composite structures. Not only allow us to reduce the weight, but that has enabled us to design new structures which allow us to get even more aerodynamic efficiency in the wings and the fuselage of the airplane.
So talk to me about composite materials. What are some of the advantages?
Composite materials have much higher strength to weight ratio than metallics. A program that we've been working with the Air Force Research Lab is, as shown in the airplane behind us, where we have applied these technologies to really improve our manufacturing capability so that the next generation of military, tactical, and transport airplanes can take advantage of these materials and show an improvement in their overall efficiency.
So this plane behind us, it's composite.
Yeah, in fact, most of it has been completely redesigned and remanufactured out of composite structure. We took a commercial airliner and we cut it off at the flight deck. We kept the wing, but everything else has been completely redesigned and built out of composite structure. So the fuselage and the empennage, as well as the tail, have all been redesigned and rebuilt out of composite. And now we have airplanes that are lighter weight and more affordable to build. One of the manufacturing leaps associated with the ACA airplane is the move from riveted structure that we used with all of our metallic airplanes to bonded structure. What this allows us to do is not only save time in the manufacturing process, but also allows us to reduce the number of parts and therefore save in design as well.
The ACA airplane is the first step in proving out the composite technologies to realize the manufacturing benefits and the weight reduction benefits of these technologies. So over the next several to 10 years, we have a multitude of technology programs in place, working both with NASA and with AFRL to mature our technologies so that by 2025, the composite aspect of our program will achieve the weight reductions and, as Jeff pointed out, allow us to build these much higher aspect ratio wings and achieve these aerodynamic benefits.
So what applications does Lockheed Martin see for the NASA vehicle?
We at the Skunk Works believe that a next generation airplane that can achieve a 50% reduction in fuel burn, greatly reduce the noise of the airplane, and reduce emissions will benefit not only the civil aviation fleet, but also the next generation of military products as well.
Guys, thanks so much. This was a lot of fun.
Hey, thanks for coming out and visiting us here at the Skunk Works today.
Thanks, man. Up next, I'm off to El Segundo, California to meet up with my buddy Aaron Drake to find out about the advanced vehicle concept design that the Northrop Grumman Company is working on. So how is Northrop Grumman involved in this project?
Well, we're one of the contractors that's doing design work for NASA. A lot of our work is on identifying not just the configurations that could represent these sort of improvements in efficiency and noise for future airplanes, but what are the technologies that enable those? What work has to be done between now and the time you actually start building those airplanes to mature all the supporting technologies that allow more efficient flight, quieter flight?
Aircraft of today are technologically very good. So what are some of the areas in which they can be improved?
Well, the airplanes of today look very similar to how they've looked for 50, 60 years. And because of that, they are very good. There's been a lot of time to optimize those airplanes, to continually improve them, to squeeze every bit of efficiency out of them. What we're looking at is taking advantage of configurations that are different than the conventional transport airplanes. Ones that maybe draw on sort of unique military heritage, airplanes that were designed for other missions. Take what's been learned from that, in particular the flying wing configuration offers a lot of efficiency advantages. Not something that's been used widely for transport airplanes, but since we have experience using it, it's one that forms a basis for developing transport airplanes that could be more efficient.
Could you tell me some of the ideas that you're putting forth to make this happen?
Well, one thing we're doing is we're drawing heavily on our heritage with flying wing aircraft. Flying wings have been around as a concept for airplanes and as a production product for Northrop Grumman for over 60 years. They offer a lot of inherent efficiency advantages, largely because every part of the aircraft actually is performing the function of flying. You're not carrying extra structure, fuselage, whatever, just to carry passengers. It's all working towards the goal of flying efficiently. We've also identified a number of technologies that are in various levels of maturity right now that with work over the next few years, we can incorporate those onto the design of the airplane to make it more efficient. One of the technologies that we're looking at is swept wing laminar flow control. Basically, technology to make the aerodynamics better, reduce drag, Laminar flow is an area that offers a lot of potential for drag reduction. Essentially what it means is designing the wing so that the air that passes over the wing does so more smoothly. When it passes more smoothly, you get less drag. This is an idea that we've used on some of our reconnaissance aircraft, but applying it to a transport like the environmentally responsible aviation aircraft is more difficult than our past applications because of the wing sweep, because of the size of the airplane.
So are you only using conventional materials or are you using composites?
Well, we're using a mix of conventional and advanced materials. There's a lot of composite construction in our concept. In some ways that's fairly conventional for military aircraft, but composites are something that are very new to transport type aircraft. Our concept makes extensive use of composites, but not in a way that is particularly risky. These are sort of conventional approaches to composites that have been well proven in military applications that allow now that benefit to be extended into transport aircraft.
So let's talk about your ABC concept, this model you have here.
Yeah, so this is, as you said, a model of our vehicle concept.
Yes.
It's actually a very large airplane. The real airplane would have a 230-foot wingspan. And in a passenger configuration, we're holding 224 passengers. We're focusing a lot also on the cargo applications of it, because that's just as important for transport efficiency. 100,000 pounds of cargo could fit inside here, and that could be anything from military cargo to letters, boxes, packages, stuff that you order. You basically can integrate this into the existing air traffic environment, just like a current airplane. Even though it's an unusual configuration, even though the wingspan's quite large, it still fits at conventional airports, it still fits on conventional taxiways because we haven't pushed beyond what some of the very largest airplanes that are out there flying today have in terms of sort of space that it takes up at the airport. And this basically takes advantage of the sort of advanced technologies like we were talking about, the laminar flow. And when we know that the airplane is going to be more efficient, we can actually reduce its size to account for that efficiency, making it smaller because it has to carry less fuel. We also talked about noise reductions. And one thing you'll notice is, unlike a lot of conventional transport aircraft, which will have their engines underneath their wings, our engines are actually integrated into the wing itself. The inlets are here above the surface of the wing. The exhausts are here above the surface of the wing. And what that means is the airplane itself is blocking a lot of that noise that's generated by the engines. And that's one of the reasons why during takeoff this airplane is profoundly quieter than existing airplanes. Another source you may not be aware of noise on conventional airplanes is the surfaces that are along the leading and trailing edges of the wings. If you fly on airliners, you look out the window, you'll see as they're getting ready for landing, things moving at the leading and trailing edges. And those are what are called high lift devices. And those are necessary in order to get the airplane to fly slow enough to have good takeoff and landing characteristics. Our airplane, though, because it's all wing, essentially has a larger wing than a conventional airplane. And that means that it can fly slow for things like landing and takeoff without having to have those high lift devices. Without having those high lift devices, it's quieter because those surfaces, when they move out on a conventional airplane, are kind of like a whistle that you would blow through. When the air blows through it, it makes noise. And by not having those, we get our airplane a lot quieter. So this is an airplane that in operational service would have something like 40% less fuel consumption than the current airplanes that are out there today, and it would be much, much quieter. So much so that if you were outside the airport boundaries, you probably wouldn't hear it during takeoff and landing.
What role do engines play in this advanced concept?
Well, engines have a huge role. I mean, obviously that's where the fuel is getting burned, that's where the thrust that's necessary to move the vehicle come from. And improving the efficiency of the engine itself is a big part of getting the overall efficiency of the airplane up. And we've built our concept around models from engine companies of what the improvements to engines over the next decade or so will allow us to do to have a more efficient, a more quieter basic engine that's in the airplane. Well, this has been a project that's been of great interest to us. The team that we have working on it is drawn from sort of all quarters of our company, and we have a really dynamic mix of people that bring experience from past projects as well as new innovative ideas. This is something that we hope sees production sometime in the not too distant future because the potential benefits are huge.
Aaron, thanks so much for having us here today.
Well, thanks a lot for coming out.
My pleasure, man. Thanks. After a quick lunch at my favorite LA restaurant, I cruised down to Long Beach to speak with my buddy John Bonet. We met where Boeing built the state-of-the-art C-17 Globemaster, where we'll be talking about what Boeing's future advanced vehicle concepts may look like.
So the ERA project of NASA asked industry to develop vehicle concepts and technologies that can reduce the fuel burn, the emissions, and the noise of vehicles entering service about 2025. Boeing's going to be using the blended wing body to achieve these goals.
You just mentioned blended wing body. Can you talk a little bit about that?
Yeah, the blended wing body is an advanced concept, different than a conventional tube wing airplane where a circular fuselage is connected to wings. Okay. In the blended wing body case, we basically have the wings blended into the fuselage, and that allows us to distribute the lift over a broader area.
What are some of the benefits of the blended wing platform?
Our current design for the ABC is with the engines on top. There have been designs where we've embedded the engines, or we put them right down on the surface, and actually some configurations where the engines are partially embedded in the upper surface of the vehicle. The advantage of that is you can get maybe some less drag, less interference, and one of the challenges with an embedded engine is the exhaust is out the back, and you don't get as much shielding of the exhaust. So our current configuration where we have the engines on the top, on a pylon, forward of the trailing edge, is put there only for acoustics. If it was only aerodynamic efficiency, we would have them hanging off the back, but you wouldn't have any shielding, and the airplane would be just as loud as a tube and wing airplane. One of the challenges is as the engines get so quiet, the noise is driven not by the engines, but by all the other stuff hanging off of the airplane, the landing gear, the pylons, the flaps. We're including low noise slats to help reduce the noise. We're including low noise landing gear. It's not just engine technologies. There are other technologies that we're incorporating on our ABC.
So tell me about the engines.
So Boeing's studying a couple different engine options on the BWB concept. The first one is a high bypass ratio geared turbofan engine, and that engine provides lower fuel consumption, reduced noise, and lower emissions compared to today's engines. The second engine configuration that we're studying is a little more unconventional, and that's a modern open rotor design. And that configuration allows us to have lower fuel consumption through better engine performance and also reduced emissions. Since 2007, the X-48B BWB first flew at the NASA Dryden Flight Research Center. Boeing and NASA researchers have methodically pushed the aircraft to over 90 flight tests to validate the data and flight control system. The team believes it has proven the ability to fly a tailless BWB aircraft to the edge of the low-speed envelope as safely as any large transport aircraft.
Hey man, thanks so much for everything.
All right, you're welcome. Yeah. Thanks so much for coming out.
Absolutely.
As we've seen, there are a lot of smart people in both the industry and within NASA that are working to make flight better for all of us. Thanks for watching. For Johnny Alonso, I'm Jennifer Pulley, and I'll catch you next time on NASA 360.
As Jen mentioned, NASA has a pretty...
That's a question that NASA's environmentally responsible,
to change the way we all fly. But to... All right, man, here we are, and we're gonna go that way. And let's walk.
All right, thanks so much. Stick around, we'll be up. Yeah, see, it's just, I could do it once and then after that.
What role do engines play in this advanced concept?
Stick around, coming up next on NASA 360, I don't know.